Hello and welcome back. In this video, we're starting section 7.5 on subspaces. The goal is to define the concept of a subspace and link subspaces and spans. So we were going to talk about subspaces, but really our goal is to tell you how it relates to what we were doing before and to apply what we were doing before to subspaces. All right, before we do that, I want to talk to you about vector space. That's going to be section 7.5.1. And that's really to kind of tell you why subspaces are there, what they mean, and how they'll work in the future. So recall that a subset, if I talk about a subset, it's a set included inside another set. So we're going to do the same thing. Similarly, a subspace is a space included inside another space. So before talking about subspaces, which is the topic for this class, I want to talk to you about vector space. So before getting into the idea of subspaces, we'll take a moment to discuss what a space is. So definition 7.5.1, a vector space is a non-empty set V with two operations. Right, there are two types of operations that I can do. First is addition of vectors, and that's going to be a plus. So for any elements V and W in V, there is an element V plus W also in V. All right, so I have a way of adding the elements of V. And the second part is I have a scalar multiplication. So for any V in V and any K in R, there is an element KV in V. All right, so I can add two vectors in V and get an element in V, and I can multiply any vector by a real number. These operations must satisfy certain rules. In fact, there are 10 different properties that they need to satisfy. For example, the addition must be commutative. I'm not going to go through the list, but a list of, they're called axioms of properties that these operations must hold, are very similar to the properties we've seen in chapter 1 for vector addition and scalar multiplication. So here are a few examples. I want to show you how this comes out. So Rn is a vector space with a standard vector operation. So in fact, that's the template, that's the model that we're trying to find elsewhere. Here's another example of a similar structure. Consider the set of polynomials. So that means I have a0 plus a1x plus anxn. P is a vector space with the usual addition of polynomials and multiplication by a real number. So I can take two polynomials and add them. I can multiply a polynomial by 3 and I get another polynomial. So the same structure that we have for Rn, we would have for this set P. And so a lot of the things we've been doing, we could do on P as well. Here's another example. Consider the set Fr of real function with the domain R. So that means the set of all functions from R to R. F is a function. Again, just like polynomials, I can add functions, I can multiply them by a constant. So Fr is a vector space with the usual addition of function and multiplication of functions by real numbers. All right, so because all of these examples have addition and scalar multiplication, everything that we've covered in this chapter could be applied to these settings. So I can talk, and you could talk about linear combinations of functions or the dimension of a span of polynomials. So this seems a bit artificial, but it turns out it's very useful. So it turns out that this generalization from the familiar vectors in Rn to function as vectors is extremely useful. We will save all of that fun for linear too. And there's also like matrices can become a vector space. And so there are tons and tons of situations where this would apply. And it turns out to be very useful, which is why we would cover it in a separate class. All right, so at this point, that's what a vector space means, and we're going to look for subspaces. So that means vector space within vector space. So here's a definition of a subspace of Rn. Definition 7.5.2. A subspace of Rn. So we're only going to talk about Rn. The other example was to show you what's coming up and why we care about it, but we're not going to spend any time working on it in a linear one. So a subset S of Rn is called a subspace if the following, I have three conditions are true. So first of all, the zero element. So the zero vector is in S. Second, I can add things in S, and you can see that is a lot like this. I can add things. So if I have V and W in S, V plus W should be in S. So I'm using the addition, the vector addition, and that should land me in S. And same thing for scalar multiplication. My subset S should be closed under scalar multiplication. That means for any V in S and any K in R, KV should be in S. All right, so your S is like a little vector space inside Rn, and that's why we call it a subspace. All right, so let's look at different sets and see if we can prove that they're subspaces or show that they are not. All right, example 7.5.2, show that the following sets are subspaces by proving the three properties, so 1, 2, 3, or show that they are not subspaces by finding a specific counterexample to one of them. All right, first example, V is x, y, z, all vectors in R3, so that x plus y plus z equals 3. All right, so we don't know much about subspaces at this point, so I'm just going to try. Let's look at the zero element. Is 0 in V? That's the first condition. So in this case, if I look at what x plus y plus z is equal to, that will be 0 plus 0 plus 0. That will be 0, not 3. That means 0 is not in V. So first condition is false, and so we don't have a subspace. As soon as one of the three conditions is false, you don't have a subspace. For it to be a subspace, you need all three to be true. Let's try a different one. I'm looking at the set W, again in R3, of all x, y, z, so that x equals 2y. All right, let's start again. Let's look at the zero vector. Is the zero vector in W? So in this case, x equals 0 to y equals 0. These are equal, and so yes, 0 is in W, and I have proven this first condition. Second, I'm going to take, let's look back. I'm going to take two elements in my set, and I want to look if the sum is still in that subset. So take V, I'm going to use it as x1, y1, z1 in W. So as soon as I say it's in W, that means this condition is true. So x1 equals 2y1. That's the condition for belonging to W. So that's the only information I have about V. Now I'm going to take a W, let's call it x2, y2, z2 in the big W. So x2 equals 2y2. So that's the information that I have right here, those two things. And now the question I have to ask myself is V plus W in my subset? So let's look at V plus W. That's going to be x1 plus x2, y1 plus y2, and z1 plus z2. I want to know if it's in W, so I'm going to look at x. That's x1 plus x2. I'm going to use the properties that we had over here. I know that x1 is 2y1, and I know that x2 is 2y2. That's what information I had. That's the information I had about V and W. And so I could write this as 2 times y1 plus y2, and that's 2y. So I do get that x equals 2y, just like the condition I have here. And so yes, v plus w is in w. All right, so this gives you an idea of what you have to do. We still need to do it for the third condition. We need to show that for any v in w and any k in r, kv is going to be in w. So let's prove that. I'm going to use the same notation for v. I'm going to use x1, y1, z1. That's going to be in w. So what we know is x1 equals 2y1. And I'm going to take k in r. All right, so I want to know if kv is in my set. So kv is going to be kx1, ky1, kz1. I want to know if it's in my set, so I'm going to check the red condition. So right here, x is kx1. I'm going to use this right here. I'm going to replace x1 by 2y1, and then I get 2ky1, 2y. And that was the condition to be inside w, and so kv is in w. All right, so that's the third condition. So I proved first, second, and third condition. Once you have proven all three, you know that w satisfies all three conditions. And so W is a subspace. All right, so this is what a subspace is. In the next video, we'll be looking at links between subspaces and spans. So please come back for that.